Thank you. So yeah, I'd like to thank the organizers for the opportunity to speak and for the wonderful workshop. I'm going to talk about the stochastic box-ball system, and this is ongoing work with Han Liu, who is also at UW-Madison. Okay. So the plan for the talk is to spend a bit talking about the usual box-ball system. Probably a lot of people here have heard of it, but there hasn't been a talk about it yet, so I'll go through all the basics. After that, I'll introduce the stochastic box-ball system, give some simulations. So what we'd like to talk about, or what I'd like to talk about, is a scaling limit for our stochastic box-ball system, but we haven't quite finished proving this, so I'll mention it, but I'll focus on a different result that we can prove, which is about pair formation. But before we get to that, let's start with the usual box-ball system. Okay, so we're going to think of having a box at every positive integer, and in some finite number of those boxes, let's say D boxes, are going to contain a single ball, and the rest of the boxes will be empty. So we'll call this a D-ball system, since there are D balls. So we can record this, well, as just a picture where we have some boxes with balls in them, or as a binary sequence. And there's going to be some dynamics on this system, where at each step of the dynamics, something called a carrier is going to sweep across from left to right and transport the balls around according to some rules. So how does this carrier work? Well, it'll go from left to right. Whenever it sees a ball, it will pick it up. So the carrier can hold as many balls as it wants, so it'll just keep picking up balls if it sees them. And whenever it sees an empty box, if it's holding a ball, it'll place a ball into that box. So if we start with this configuration of balls, okay, in the first step, the carrier will see this ball, it'll pick it up. In the second step, it'll see another ball, pick it up. And now it'll have an empty box, drop the ball. Now 3 more balls that it picks up, then drops, then picks up another, then drops the final 2. And then from this point on, there are no more balls and the carrier is empty, so it just stays empty for the rest of the sweep. So one step of the dynamics is one full sweep of the carrier. Okay. So from time 0, if we were here, at time 1, this is what we had after the carrier sweep. Okay. There's an equivalent way of describing this dynamics in terms of a vertex model. So we can consider a vertex model in which we have paths that are going up and right. And on vertical edges of our vertex model, we can have at most one path. But on horizontal edges, we can have, say, at most D paths for this D-ball system. And we assign some weights to this vertex model, to the vertices of this vertex model. And it turns out that this vertex model is Yang-Baxter integrable. There's a Yang-Baxter equation for these weights. So we don't want quite this. We want to take the limits as Q goes to 0. So when Q goes to 0, we have 4 types of vertices and that survive in this limit. These are their weights. And usually, the R matrix you get, so the matrix of weights that you get when you take this limit is called the combinatorial R matrix. Okay. And in this limit, the dynamics of the box-ball system are just like coming from the transfer matrix of the vertex model. So wherever we have a path entering on the bottom, that corresponds to balls on this bottom row. Whenever we have a path exiting on the top, that corresponds to balls at the top row. And the number of paths on the horizontal edges corresponds to how full the carrier was as it did its sweep. Okay. And there's a rich world of connections between these integrable vertex models and the box-ball system. Right? So this is very classic stuff. And kind of the main thing, one of the main things people are interested in the box-ball system is the presence of solitons. So solitons in this context are going to be just chunks of balls. So say here we have a 4 soliton. And under the dynamics, they're going to move at speed 4. Right? So the carrier will just pick up all 4 of these balls and then immediately deposit them. So this chunk of balls will move at speed 4. And sort of more importantly, these solitons maintain their size and shape when they collide. So here we have a 3 soliton and a 2 soliton. And sometime around time 2, they collide. So there's some shifting from the interaction of the collision. But then afterwards, the 3 soliton continues moving at speed 3, and the 2 soliton continues moving at speed 2. So in fact, like the original motivation of the box ball system was to study the KdV equation in which solitons there take the form of solitary wave solutions. Okay. And it's known that if you start from any configurations, any initial configuration, and you run your dynamics for a long time, the system will decompose into solitons of weakly increasing length. So for our example, if we run it for a few more steps, what will happen is we'll end up with 2 1-solitons, so these will just move speed 1 for the rest of time, and then this 4-soliton at the front, which will move at speed 4 for the rest of the time. So this initial configuration decomposes into solitons of length 4, 1, and 1. Right? And usually people encode this information in a Young diagram, where the first column is the length of the longest soliton, then the second column is the length of the second longest soliton, and so on. So one way to add randomness to the system would be start from random initial conditions. And if you do this, you can ask a lot of questions. One class of questions people ask is, what does the soliton decomposition look like for some choice of random initial conditions? So there are many results on this, or results of the form, what does the limiting Young diagram look like for these sorts of things? So there was work on the basic box ball I described, but also generalizations where you have colored balls that behave in certain ways. And another thing you can ask is, what are the invariant measures for the box ball system? So if I start with some initial distribution, what distributions are preserved under the dynamics? Okay, and there's also a lot of work on this. But we'll be studying a different way to introduce randomness to this system, and I'm going to call it the stochastic box ball system. So what we will do is, we'll fix d balls just as before, but now we'll have some parameter epsilon in 0 to 1, and epsilon will be the probability that our carrier fails to pick up a ball. Right, so now instead of having a carrier that always picks up balls, it's now faulty, so sometimes it messes up and it just leaves the ball in place. Okay. So this failure chance is going to be applied independently for every ball the carrier sees. So for example, in this simple situation where I have 2 balls, normally these would both just get picked up and deposited 2 spaces over. But now you can say, skip picking up the first ball and then pick up the second ball, and you'll end up with this configuration here where they've spread out a bit. Okay. So that's a system that we'd like to study. So here's a simulation where we start with 5 balls at time 0, and epsilon here is 1/2. So half the time a ball is picked up, half the time the carrier fails. And you see that this 5-soliton, of course, no longer has a preserved shape or speed. It just disintegrates into a bunch of kind of single balls and pairs, I guess. This is kind of clearer to see if you make epsilon very small and start with a large number of balls. So here we're starting with 50 balls and epsilon is 0.01. And this bottom envelope here is this, first starts off at this big chunk of 50 moving at some high speeds under the dynamics. But very rarely, some ball will break off from this big chunk, and then it will continue in just a straight line with speed 1 minus epsilon. So not 1, because there's some probability that it doesn't move at all. So some average speed of 1 minus epsilon. So these are these straight diagonal lines. But occasionally, 2 single balls will form a pair, and they'll kind of speed up for a little bit before breaking back apart into singletons. So this is kind of generically what you see when you run the simulations. So here's a close-up on this kind of pair formation. So we have 2 balls, they're moving as a pair. Then after some geometric amount of time, they're going to break apart. And then eventually, they'll reform again into a pair, stay as a pair for a bit, and then break apart. And this process kind of repeats over and over again.
Why would they merge again?
So you can show just using a gambler's ruin type argument that almost surely they'll rejoin. But if you start with the 2-ball system, the time it takes, or the expected value of that return time will be infinite. So it's some null recurrent random walk. Okay, so I want to talk about some limiting values of this, this failure probability. So of course, if there's no probability to fail, then all the balls get picked up, and this is just the normal box ball system. So when epsilon is 0, you just get the usual box ball. But if you take epsilon to 1, then the carrier will tend to always fail. So normally, just nothing is happening. All the balls are staying in place. But for each ball, there's some geometric clock. When that clock rings, after many, many steps, that ball will get picked up, and it'll get carried to the head of whatever stack of balls it's currently in. But instead of thinking of that ball being transported, we can instead think that it jumps one space to the right and pushes all the balls in front of it. Right. So in the limit, after you appropriately rescale time and take epsilon to 1, what you get is that you have an exponential clock for each ball, and when that clock rings, it pushes everything in front of it one space to the right, which is exactly this push-take subsystem, if you know about it. And this is some integrable particle system. So somehow our stochastic box ball system interpolates between two integrable particle systems, the normal box ball and push-take sub in the limit of its parameter. So originally, when Han and I decided to try to study this model, we were hoping that we'd be able to do some nice integrable probability. Maybe we could relate our dynamics to some degeneration of a stochastic vertex model or something like this. But we were not able to make any of that work. So some questions I have is there actually some integrable structure underlying this dynamics? Yeah.
So you would have another way to add randomness, like always pick up the ball, but you would say drop it sometimes?
Yeah, sure. So actually, the first thing we did was we had two failure probabilities, a failure to pick up and a failure to drop. But this was just more complicated, so it was easier to just always. No, because if you have a failure to pick up, right, the ball will get picked up and then it'll get dropped in the next spot. So the most it can move is 1, right? But if you have a failure to drop, then you get picked up and you can get transported very, very far away, right? So the system has, just very different features, I guess, depending on the two. Right, so we were hoping to do some integrable probability, but we didn't quite succeed in this. So maybe there is some integrable structure that we just didn't find, or maybe there's a more clever way to add randomness to the dynamics of this model that will preserve some of the integrable properties in a more obvious way. So those are some questions I have that we didn't figure out. Okay.
When you had the vertex model before, that was not positive, I guess, when Q is.
It's not a stochastic vertex model. Yeah. So
it's not like a stochastic model that converges.
Exactly. So that's what we tried at first. Maybe start with a stochastic model, perturb some parameter, and see if we can match it up with what we have. But I just couldn't make it work. Yeah.
What happens if you limit the capacity of this container?
Yeah, so that is something people actually do pretty often for the box ball. So by limiting the capacity of the container, you get a different vertex model, right? Because you have a different spin on the horizontal edges. And from the commuting transfer matrices, this gives you some conserved quantities of the dynamics for normal box ball. And then by using various capacities of the carrier, you can you can get a lot of information out of that. I don't know all the details, I guess. But this is something people do, and it is useful. Yeah.
Yeah. So Thomas Lamb once suggested that you try to take Q equal to 0 with the quantum proof R matrix. Did you try that?
So sorry, for which?
If you take the quantum proof that's under a stochastic vertex model, that the Q goes to 0, you're supposed to recover usual box ball.
So if you start with the
we turned it into a coupled parallel matrix.
Right. So for the box ball system, that's how you get it, right?
Yeah.
But when we Yeah, I don't know exactly what will happen if I just do that directly for
Yeah, I don't know
stochastic
either.
weights. Yeah.
That's good.
Okay. 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 So this is what we wanted to do. We didn't quite succeed, but now I guess I'll start talking about what we actually did. Okay. So with the model we have, what can we say? So rather than looking at the ball positions, I want to look at the spacing between them. So if my ball positions are at, say, zeta 1, zeta 2 to zeta d, I want to look at the gaps, zeta I plus 1 minus zeta I minus 1. So this just means the number of empty boxes between pairs of balls. So this is, I'm going to call the interdistance process. So for example, if I have these 4 balls, here's W1, W2, W3, just the number of empty boxes between the balls. So the dynamics of the stochastic box ball system are translationally invariant. So it makes sense to ask about the dynamics of these spacings, right? I can just run the carrier, see how the spacings change, and then say shift everything back to the origin. So we'll think about the dynamics being governed by a sequence of independent biased coin flips. So we flip a coin for each ball. That tells you whether or not the carrier picks it up. You run the carrier through, and once you know whether or not you're picking up the balls, their positions where they land will be determined. So the dynamics is controlled by just these sequence of coin flips. And one thing I want to point out, we don't actually care which ball is which. So when you're running the dynamics, it could be that this ball eventually overtakes this second ball. For us, that doesn't matter. We're always just looking at the sequence of interdistances. Right? So I don't care whether or not the balls swap position. So this is going to give us some Markov chain on zd minus 1, the positive orthant of zd minus 1, if I have d balls. Okay, so the simplest case would be if I just started with 2 balls. And we can look at the increment of this Markov chain. And you'll find that if the balls are spread out, so we're not at 0, we're in the bulk, then this behaves just like a lazy symmetric random walk. Right? And it gets lazier as our failure probability moves away from 1/2. And then when you're at 0, there's just some boundary behavior on how it behaves. So as Leo asked earlier, you can just use some gambler's ruin problem to say that the time it takes for pairs to reform, well, they'll reform almost surely, and the time it takes on average is infinite. And of course, they'll break up after some geometric amount of time with average 1 over epsilon, 1 minus epsilon. Okay. So this is the simplest case. We have this 2-ball system. And here's kind of what a trajectory of W1 looks like. So here's time. We ran it for 5,000 steps. And here is the spacing. Okay. The next simplest case would be, here's another, So here epsilon is 0.5. But as I move away from epsilon equals 1/2, the walk gets lazier. So you start seeing more kind of flat steps where it's just staying in place. And if epsilon is very, very small, the walk is very, very lazy. And it stays a long time at a given height before it moves. So the next simplest case besides the 2-ball system is the 3-ball system. So here are the increments for the 3-ball system. So here is when the balls are all spread out. So these sequences here are the sequences of coin flips. So for example, if I succeed in picking up the first ball but fail on the second 2 balls, what will happen is this first distance will shrink and the second distance will stay the same. So we'll move in that direction. W1 will decrease and W2 won't change. So any sequence of coin flips I don't show here corresponds to a sequence in which the spacing doesn't change. So for example, if I pick up all 3 balls, if I have 1, 1, 1, then the interdistances don't change. So then you just stay there. So I don't draw those numbers because the picture gets too cluttered. Okay. So the interior behaves like a lazy symmetric random walk, this time on Z2. But then there are some boundary behaviors that have some remnant of the soliton behavior. right? So when I'm on a boundary, say I'm on this boundary where the first two balls are grouped together, then it's possible for these two balls to move at speed 2 and increase this gap faster than you can get in the bulk. And this is coming from what remains of the solitons for this system. And in general, for a D-ball system, you see the same sort of thing. So when none of the balls are together, when you don't have any pairs, when you're not on a boundary, it behaves as a lazy symmetric random walk. But when you're on some boundary, then you have some remnant of the soliton behavior that makes things a little bit more complicated. Okay. So here's a trajectory of the interdistances for some 3-ball system. And if I make epsilon small, then, when epsilon is small, the failure probability is small, so kind of the soliton behavior gets preserved more. And you see when you're hitting this axis, that's when you're in this case where there's 2 balls in front or together. So they'll tend to speed up and push you further along this axis. So that you hit the axis, stay there for a while, then you'll leave the axis and kind of meander around. Then when you hit the axis again, you speed to the right some more. So this is what happens when epsilon is small. When epsilon is large, then you're just very lazy. The walk tends to not pick up any balls, so you kind of stay in space or stay at the same spot for a long time. Okay, here's a little video if it runs. Oh yeah, so this is epsilon 0.5. This is what the interdistance process looks like in some simulation. Hopefully it'll hit some axis, and you can see that it'll shoot in one direction, coming from this remnant soliton behavior. Yeah, see, when it hits an axis, it kind of speeds along in a single direction. Okay, I don't know how long this runs for, actually, but I think you get the point. Okay, so what our goal is for this project of Han and mine is we wanted to show that when you take an appropriate scaling, that this interdistance process converges to a reflecting Brownian motion, a semi-martingale reflecting Brownian motion. So unfortunately, we haven't quite finished showing this. So with time permitting, at the end, I'll kind of explain like where we're stuck at the moment. We're very close, but not quite there. But before that, I'd like to talk about a result about pair formation, which is actually important for the proof of the thing I'd actually like to show that we haven't finished. So what we can show is that for any of the pairs of balls, the distance between them will reach 0, order n to the 1/2 times on average in n steps. So for a simple random walk, this is just simple, it's true, it's sort of easy to show for a simple random walk. But for our case, this remnant soliton behavior makes this a little bit non-trivial, because if I hit this axis, I kind of shoot towards the other axis. So I have to be able to control the extra number of hits I'm getting to the axes from this bias that you get. So there's a little bit of some combinatorial intricacy to actually bound the number of extra hits to the axis. So I'd like to kind of walk through that proof, because I think it kind of shows a lot of the subtleties of the dynamics of this, and I kind of like it. Okay, so the main idea is we're going to take some pair of balls, and we're going to couple it with a 2-ball system. So a 2-ball system is just a lazy symmetric random walk. So we know everything we want about it. So if we have a nice coupling, then we can use what we know about this 2-ball system to tell us about the pair spacing in the D-ball system. And the way we'll couple it is just that we'll use the same coin flips for the pairs of balls. So if this first ball gets picked up in our D-ball system, the first ball gets picked up in the 2-ball system. So that's the coupling. And for the first pair of balls, it's easy to check that the presence of these extra balls to the right only serves to make this distance grow faster. So all they can do is make this ball speed up when it's going to the right. So we know that for all time, the spacing W1 will be bigger than the spacing for Z1. And this lets us bound the time that W1 spends at 0 bounded above by the time Z1 spends at 0. And because Z1 is just a lazy symmetric random walk, we know that the time Z1 spends on 0 is square root of n on average, if we want to spend steps. So that's nothing hard.
Sorry, but it's the upper bound. But how about the lower bound?
Yeah, I actually don't know. I haven't tried to look at a lower bound.
But you don't need the lower bound.
I don't need the lower bound. Eventually, for the scaling limits, we're gonna have some error whenever we hit, whenever a pair of balls forms, and I need to know that when I divide by square root of n, it will be small enough. Yeah. So I need to know that this will be small compared to square root of n. We'll see. Okay. So for the first pair of balls, this is easy. But for the interior pairs of balls, this becomes more complicated. Because now, on our D-ball system on the top, we have these extra balls to the left. So these balls can cause this distance to shrink faster than Z1. Right? So we no longer have this domination where I can guarantee that Wi is going to be greater than or equal to Zi. Now that won't always be true. Right? But what will be true is I can upper bound the time Wi spends at 0 by the time Zi spends at 0 plus some extra hits. Right? So I need to control how many extra hits I get from the balls on the left causing this distance to shrink faster. So to do this, we'll break this walk up into pieces. So we'll look at first the time the first pair on the left forms. So if there are no pairs on the left of this ball, then it's getting no influence from the left. So by the same arguments as before, Wi is going to be greater than or equal to Zi. But after some pairs form with these left balls, these could speed up and this distance could close quickly. So after time Ti, I can no longer guarantee I have this domination. Okay. And another thing to note is that once these balls form on the left, there'll be some amount of time gamma 1 until they break apart into singletons again. So what I need to control is how many extra hits I get to 0 in this interval. So in the interval T1 to T1 plus gamma 1, this ball will speed up faster compared to this ball here. And I have to control how bad that makes things. Okay. So let's look at a next time T2. So we have some pairs forming on the left at time T1. They stay together up until T1 plus gamma 1. Then they break apart. And now at some time T2, they'll form pairs again. So we have another chunk of time where there are no pairs on the left. But now we don't know that Wi is greater than or equal to Zi because the pairs on the left previously could have messed up that domination. But in this new interval, we still have that the increment is well behaved. So in this new interval from T1 plus gamma 1 to T2, where there are no pairs on the left, then the increment is well behaved. And if any point Wi becomes larger than Zi, then we preserve our domination for the rest of the interval. So I just need to count the number of extra hits up until the point that Wi is greater than or equal to Zi and show that this is something not so big. Right? So in principle, it could take a long time before Wi is greater than or equal to Zi again. But we can show that the number of extra hits you get to 0 in Wi, the number of extra times Wi equals 0, is not going to grow so big, even if that time takes a long time. So what you can show is that because the increment is well behaved, that if Wi is at 0, then Zi has to be at its running minimum. So for example, if this is what the spacings look like at time T1 plus gamma 1, Okay, wi goes down and hits 0. Zi goes down as well because the increments are well behaved under this coupling. So it's at its running minimum. And now, say wi can increase by a lot. Say it increases by 2. Zi can only increase by 1, but since the increments are coupled well, it will also go up. And now for it to reach, so for wi to reach 0, Zi has to go past where its previous running minimum was. And so now when wi hits 0, Zi is at a new running minimum. So you can bound the number of extra hits we're getting to 0 for wi by the number of times that Zi hits its running minimum. And then you need to show that, okay, every time it hits its running minimum, there's some probability that the next step takes it lower. So it can only hit each level of its running minimum, like each of these levels, a geometric number of times. So the point being that even if it takes a very, very long time for for Zi to catch up with wi and for our domination to be preserved, the number of times wi can hit 0 in that period is going to be something finite. It's going to be a sum of geometric random variables. Okay, so that's the point. We can bound the number of steps for which wi is 0 by the number of steps which Zi is 0, plus these extra hits when we don't have good domination. But these extra hits are bounded by a sum of geometric random variables, so it's small. And now, okay, we can look at this expectation, and we'll have that the expected number of times wi hits 0 is going to be the expected number of times Zi hits 0. Well, that's just a lazy symmetric random walk. We have good control over that. Plus the sum of these extra hits over all of these intervals. So each of these, in a given interval, the number of extra hits is some geometric random variable, or bounded by a sum of geometric random variables. It's bounded by just some constant. And then the number of intervals, well, by induction, the number of intervals is just the number of times we had, or is bounded by the number of times we had pairs form in the left balls. And we know by induction that that is square root of n, or order square root of n. So in the end, we get something that is bounded above by some order square root of n. So that's the proof for this. Right. But what we actually care about in my last 5 minutes, I'll briefly, when does my talk go till? I have 15, okay, yeah. So in the last few minutes, however long this takes me, I want to talk about what we're trying to prove, the scaling limit for the interdistance process. So we want to show that under appropriate rescaling, our interdistant process converges to a semi-martingale reflecting Brownian motion. So what does this mean? So this means that we can decompose our process, so in this case W, into some interior process which is going to behave like a Brownian motion. So in our case, our interior process is when all the balls are spread out and we have some symmetric random walk, which in the limit will become some Brownian motion. So we can write our process as this Brownian motion bit plus a reflection part whenever you hit the boundary. So Y here is going to be some d minus 1 vector. So yeah, if we're in zd minus 1, that yi will just kind of keep track of the number of times we hit the boundary wi is equal to 0. So every time we hit that boundary, we'll have some reflection matrix that pushes us back into the interior. So W will only live in the positive orthant. X will be defined on the whole plane. And then R times Y is this boundary process that's pushing us back into the positive orthant for W. So there's just a whole bunch of theorems by Williams and collaborators that tell you when you have some process that can be written in this way, how it converges to this semi-martingale reflecting Brownian motion. All right. So what we'd like to do is just use one of these theorems and get our result. But we have this issue about our reflection matrix. So for these theorems, so normally when you're proving something converges to an SRBM, you need a deterministic reflection matrix. And in particular, your reflections always have to point inside. So when you hit a boundary, you always have to be pushed back inside to the positive orthant. But for our process, our reflections are random. When we hit a boundary, we just have some random reflection, and sometimes these reflections will push us along the boundary. This is coming from like just the speed up from the solitons. You can just push us quicker along the boundary direction. So we have to somehow rectify this. So here is our, say, if I take delta y to just be counting the number of times I hit boundary I, then our R matrix, our reflection matrix here, is just completely determined by our process. We know the increment of W. I know the increment of the interior process. It's this symmetric random walk. So I can determine what R is. And R will depend on what coin flips I have when I reach a boundary. So we have this random reflection matrix. And sometimes the reflections will push in the direction of boundary, which is also not something good. Okay. So our idea was, instead of looking at the reflection matrix we get this way, we should just replace it by its average. So replace the reflection matrix by the average reflection matrix. And when we do this, every time we hit the boundary, we're going to pick up some error from this replacement of R by R bar. And so now our decomposition will be like W is this interior process plus this average reflection plus a sum of error terms from the replacement. And we'd like to show that these error terms are small. But we can do this by using this pair formation result we have from before. So every time we hit a boundary, the reflection is actually an IID random variable. It doesn't depend, for the most part, okay, I'm kind of lying, but for the most part, it doesn't depend on where you hit the boundary. It just depends on what boundary you hit, right? So this error is going to be a sum of mean zero IID random variables. So we can use the central limit theorem and bound how big the size of the sum is. And in fact, it will be square root of the number of times, or the number of variables we're adding up, right? That's what the central limit theorem tells us. And this time, the number of variables we're adding up is exactly the number of times we hit the boundaries. And as before, from before, we showed that the number of times we hit the boundaries is O of n to the 1/2. So the square root of that will be n to the 1/4. And since we're scaling everything by n to the minus 1/2 to take our scaling limit, this error term will actually be small and just vanish. So this replacement with the reflection matrix by its average kind of doesn't introduce any error in the limit. The error vanishes in the limit. So this is all nice, but the issue we have remaining is that I kind of lied, and the reflection matrix, or the reflection does depend on where you are on the boundary, but only very, very close to the origin. The reflections only change when you're very, very near the origin. And in that case, we'll have some additional error from replacing R by the reflection matrix by its average. And we need to show that this error doesn't contribute that much. So we need to show the number of times you hit very, very close to the origin is little o of n to the 1/2. So for a 2D symmetric random walk, the number of times you hit the origin is log n. It's very small. And this seems to be true for our system as well, but it's been difficult to actually show this because it's hard to couple with a symmetric random walk because of this remnant soliton behavior. So it should be true, and simulations indicate that it's true. So this is the log of the number of times that you hit the origin compared to the log of n to the 1/2. So this is just in a log plot. So this is just a line of slope 1/2, and the number of times we hit the origin by time n really seems to be growing much smaller than n to the 1/2. So it should be that the extra error we get near the origin is small, but I haven't been able to make this precise. Okay. Yeah, so thank you for listening.